Hello and welcome again to my Physics Online video lecture series. In today's video, we're going to be discussing blackbody radiation. And so this is sort of an ongoing set of lectures that I'm preparing about topics of interest, basically turn of the century, 20th century, up into maybe middle of the 20th century, what is often called modern physics. And some of this stuff, of course, is also predates the 20th century. It's still labeled as modern physics, so take that title with a grain of salt. I'm going to kind of give a survey here of blackbody radiation because it's a complicated enough topic that there's sort of like the classical and thermodynamics part of it, and then there's the Planck contribution and energy quantization for photons, which is why we're interested in it for modern physics. I usually actually don't get to radiation when doing thermodynamics in my classes, and so if I were to have it, it would be kind of a thermodynamics topic and would be actually a physics 1 topic. And then as a survey of modern physics, it's kind of like physics 2 plus, shall we say. It's like this is the last week of physics 2, but we have to refer to something that would hypothetically be taught in the last week of physics 1 if we had time to teach all the things in physics 1. So I don't know if it's really fair to have a recall section here, because most of you coming to this video, if you've watched through mine, you're not recalling it. But you may, if you've done some physics 1 extra reading, that kind of thing, have looked into different types of heat transfer. You may know or be familiar with the idea of radiation. And so radiation basically involves emission of electromagnetic wave. Now classically, we knew, without any quantum mechanics, we knew that the hotter the object gets, the more energy it's going to emit per unit time, and B, we also know that the color kind of changes for the emission. If you heat up a metal a bit in a furnace, you might bring it out and it's like red hot. Well, if you heat it up even more, you might bring it out and it's orange hot, or blue hot, or what we might call white hot. Usually it's white hot, not blue hot, but the peak emission may be in the blue if you've heated it sufficiently. You may be melting it depending on your metal though. So you know that there's red hot, you know that there's kind of like orange hot, yellow hot, and then sort of like white hot. Color changes as the thing gets hotter. And at the same time, the amount of radiation, the power, also increases as you make the temperature higher and higher and higher. And so it turns out that that follows what's called the Stefan-Boltzmann equation. The rate at which energy is being emitted or absorbed, Q over T, the power if you will, is given by the emissivity or absorption coefficient, times essentially sigma, which is the Stefan-Boltzmann constant, times the surface area of the object, which I'm using an A here since S might make you think of the pointing vector, times the temperature to the 4th power. All right, so the Stefan-Boltzmann equation basically says that as the temperature of the object increases, the rate at which it emits increases by the power of 4. So if you double the temperature of an object in Kelvin, then you don't double the power it emits at, you don't quadruple it, you don't 8-fold times it, you actually 16-fold increase the emission power. And as it turns out, this can be generalized because this is sort of emission. If you have absorption due to the environment surrounding the object, then this equation maybe generalizes to rate at which the, let's say, energy in the object is changed. And it's the same three initial terms, and then instead of just having a temperature, you have temperature of the object to the fourth minus temperature of the environment also to the fourth power. And so this right here is the sort of like the true rate at which energy is being lost from the object, the rate of change of the energy in the object. And it could be actually gaining energy too if the environment is hotter than the object. All right, so that's radiation as such. Now, the next thing is that I mentioned earlier the sort of like wavelength changes depending upon how hot you make the object. But it's actually more complex than just saying that, because objects don't emit at just one wavelength. Rather, they emit at a bunch of different wavelengths. And this is kind of characterized originally by the Rayleigh-Jeans. So Rayleigh and Jeans. And their characterization basically says that the intensity emitted is going to be proportional to the inverse of the wavelength, actually to the fourth power. In other words, this is basically what they were able to characterize the spectrum of from measuring essentially the visible spectrum of the wavelengths being emitted for a very hot object. This is sort of like classical prediction. But there's a problem with this classical prediction, which is that we have here a lambda to the fourth power. This is occurring at a given temperature, and it's occurring for a spread of wavelengths. So T is just some constant number for this emitter. But it's emitting a bunch of wavelengths. And this prediction right here says that as lambda approaches 0, in other words, as wavelengths get shorter, the intensity should approach infinity. In other words, we should have infinite emission in very, very short wavelengths. This was nicknamed the ultraviolet catastrophe sometime after the fact. It's not really UV that you would go to infinity, but you eventually get infinite intensity being emitted from any object at any given temperature once you get to sufficiently short wavelengths. And so that doesn't work, because that essentially means everything should be emitting infinitely much energy. But we know that that's not the case. So that's where Planck kind of came into things. Planck's hypothesis basically says the energy of atomic oscillations is quantized. And what that basically means is that the emitted waves are also quantized in energy. Now the equation that goes with that is that the energy is h, Planck's constant, times F. All right, in other words, the emitted EM waves, the waves that are being emitted are electromagnetic radiation. They have to have frequencies. It has some frequency, and the energy is quantized. It can't just be any arbitrary energy in that wave. It has to be somehow the frequency of the wave times h times some number. So there's some number of particles allowed. So in some sense you could say this right here is the energy of one particle. So this is one, maybe I shouldn't say particle, we could say one quanta or one quantum of EM energy. And then the total EM energy, E total, at a given frequency would be how many quanta there are times h times f. Now, in terms of the wavelength, we know that wavelength is related to speed and frequency. These can be rewritten so that E for one quanta is hc divided by lambda, and therefore, so this would be like E for 1. Therefore, the total would be N times hc divided by lambda. All right, so how does this resolve this ultraviolet catastrophe? This quantization of energy basically means that you can't have, partial, call it like partial amounts of energy. You either have to have 1 or 2 or 5 or whatever of these quanta, or 500 billion, or etc., etc. It also means that these have to be emitted in the form of basically a photon containing an energy equivalent to one of these, HF, 2HF, 3HF, etc. Okay, so far so good. Now, in this ultraviolet catastrophe, if we come over here, this is saying that as the wavelength goes up, the intensity emitted goes up, up, up. The modification that Planck's hypothesis makes to this is basically by saying you have to be able to actually emit photons in order to essentially get radiation at that frequency or at that wavelength. Now, those photons are being emitted by basically the atoms in the emitter, by their having some amount of heat. And we know that they have some heat energy proportional to K times T. Okay, so basically your energy for a given excitation is proportional to kBT, basically times 1 or times a half or times 3 halves, depending upon your degrees of freedom in your system. Now, the relevance of this is that this quantity right here, this corresponds to energy of one quantum. It's basically how much energy is there available to generate parts of this wave. So if we have a very low, small wavelength for a high frequency, if F is large or lambda small, then it would follow that H times F might be greater than your K sub B T, or your F over 2 K sub B T. And what that means is you won't really be able to emit photons in that particular frequency. And in fact, before you get to that frequency, the number of photons emitted has to be fairly small because the energy per photon is very large. So you don't have as many photons to be emitted, And this intensity thing, it has to be emitted in all directions. So you end up not having very many photons emitted if F is large compared to if F is small for the same energy cost. All right, so taking these basic ideas and sort of recombining them with the Rayleigh-Jeans sort of law, and I should note the Rayleigh-Jeans law, again, did a pretty good job of matching what was observed at long wavelengths. It was, I think, actually derived from empirical evidence using relatively long, like visible and IR type wavelengths. So in order to reconcile these things, Planck then had to remake a law for blackbody radiation. We call it the Planck's law for blackbody radiation. And so this new law, this law has an equation to it. Rather than just being intensity or irradiance or what have you at a given temperature, it has temperature and wavelength built into it, thanks to the sort of Planck hypothesis, E equals HF, such that this now has, yes, a factor of lambda, albeit it's lambda to the 5th power in the denominator, but also an exponential term factoring in the k sub b times t factor. So the equation basically ends up being a function of t and lambda. It's 2 times hc squared over lambda to the 5th times 1 divided by the natural number to the power of hc divided by lambda times kbt. Note that hc over lambda, that part of it is just an energy. So you're basically dividing the energy here of a photon, a quanta that's being emitted for this electromagnetic wave, by the energy of your actual black body. I've been saying intensity throughout this as a simplification. It's actually defined, by the way, as irradiance, which is fairly similar actually to intensity. It's basically power emitted per unit area, per unit steradian, per unit wavelength. So note that intensity is power per unit area. So we're power per unit area of the emitter per unit steradian, which is sort of like the per area of the regular intensity equation, just moved to solid angle, per wavelength. This factor in the exponent is the quantized energy, that hc that Planck came up with, divided by the thermal energy. So we're basically making use of E quantized is HF is HC over lambda, and E thermo in this case is K sub B times T. Essentially you're emitting from the surface area, and so you have 2 degrees of freedom, and so that factor of F over 2 is just 1. Alright, so that is the Planck's law. I have actually plotted it. I wrote something in MATLAB to plot this, and so I'll show that to you, but I'm going to show it without much in the way of further comments. That could be for a separate. Alright, so this is basically your plot. This is taken at different temperatures. For some reason, the actual axis numbers got cut off. As it turns out, I did this such that each of these little tick marks down here represents 500 nanometers worth of wavelength, and the temperatures that I happened to plot were 2000 Kelvin, 3000 Kelvin, 4000 Kelvin, 5000 Kelvin, 6000 Kelvin. 6000 Kelvin, for what it's worth, is basically the sun's surface temperature approximately, for what it's worth. So notice that this peak happens just past 500 nanometers, which is right here. And so this peak is roughly green. as it turns out, or yellow-green. And so, as it turns out, this whole spectrum is from about here to about right here is the visible part of light, and therefore the main spectrum from the sun is visible, and thus we have a sun that looks kind of yellowish color, but also like white. Don't go stare at the sun to verify this statement, please. Okay, so this is what the plot looks like. You could say this is Planck's law plotted. And that's all that I'm going to do in today's video. It's a little more survey-ish, but that's going to be the nature of most of these videos with modern physics for me, I think, for now. Hopefully you enjoyed it. Hopefully you learned something from it. Hopefully it inspires you to go read a little more about it as well. In the meantime,